All right, we're dealing with drag force today, and uh, remember where drag force comes from. Anything that moves through a fluid, any gas, any liquid, it's going to collide with the molecules of that fluid, and every collision, uh, every time a molecule hits the fluid, that's a tiny little backwards push. And the total of those billions and trillions of backwards pushes might amount to a significant amount of backwards push, which would be a significant drag force. So we're considering specifically here drag force through the atmosphere. Drag force through other kinds of materials will uh, uh, involve slightly different factors, but for drag force through the atmosphere, the magnitude of that force is just equal to these factors, 1/2, and then this thing that looks like a P is the Greek lowercase letter rho, and that's our usual symbol for density. In this case, that's density of the atmosphere that that our object is moving through. Uh, you get higher density at lower elevations and lower density at higher elevations in the atmosphere. The next factor, CD, is the so-called drag coefficient that has to do with how smooth or how rough the surface of the surface of the object is. Area is a cross-sectional area of the object. By cross-section, I mean look at the direction of motion of the object and then take a slice of the object perpendicular to the direction of motion. That, for example, if you're looking at a sphere that's falling, all of the lower half, the lower hemisphere of that ball is going to hit air molecules. The lower half is the part of the ball that's going to be feeling the drag force. So, so obviously, if that area is bigger, then more molecules hit the ball per second, and it's a stronger drag force. Area specifically is just a measure of this much area. In other words, draw an equator for that ball, and then imagine taking a slice of the ball along the equator. The area of the circle, this circle whose circumference is the equator of the ball, that area is the relevant area that's perpendicular to the direction of motion. That's what we call the cross-sectional area. Just take a slice of the ball along that equator, and that's the cross-sectional area that goes in the A spot. And then, of course, the last factor is velocity squared. Now, for our purposes, we're just imagining a simple model here where we're always watching a ball move through the same part of the atmosphere. We're not trying different elevations. So always in the same part of the atmosphere means density is always the same, and we're using the same type of ball. So the drag coefficient is always the same, and the size of the ball is always the same. So this area factor is always the same. The only part here on the right-hand side that's going to change is v squared. So now in this case we have a proportionality, a so-called direct proportionality. We can write this equation in a simpler way. Magnitude of the drag force equals just constant factors times v squared. That's an example of so-called direct proportionality. Anytime you got two variables that are related like this, one variable equals a constant times the other variable, you have direct proportionality. So let's think about how that direct proportionality actually works. Let's say in one particular case, let's say when one of the variables has a value of 1/2, the other one turns out to have a value of 4. So when these are the values, then this equation looks like 4 equal to c times 1/2, and of course that tells us what c is. C has to be 8. So this implies c is 8. And now try some other variables and let's see the pattern here. Let's try for our next value of x, something that's twice as large. Twice as large as 1/2 is, of course, 1. So our second value of x is 1, which is twice as large as the first value of x. So y equals c. C is 8. And then times x. X is now 1. So the second value of y is what we get when we put the second value of x in that equation. And it's 8 times 1, or y2 is then equal to 8. And try one more here, and then you'll see exactly how this works. Our third value of x will be now 1/4, which is half the size of our first value, which was 1/2. So now the third value of y is what we get when we plug the third value of x into our equation. So y3 equals 8 times 1/4. So third y is now just 2. And now we see the pattern in direct proportionality. Going from the first xy to the second xy pair, x doubled. X went from 1/2 to 1. X doubled. Right? The new x was twice the old x. And then what happened to y? The first y was 4. The second y was 2. Y also doubled when x doubled. And then here, compare this with the very first xy pair. This value of x, this new value of x is 1/2 the original x. And then the new y that you get out of that is 2, which is also 1/2 of the original x. The original x was 4. So here, one variable changed by a factor of 1/2, and then the other variable also changed by a factor of 1/2. Right? Here, both x and y changed by a factor of 2. Here, both x and y changed by a factor of 1/2. That's the way it always works with direct proportionality. Right? In direct proportionality, when one variable changes by some factor, that is, the new variable is this number, this factor, times the old variable, then the other variable must change by the same factor, So the pattern would simply be like this. New value for one variable equals some factor times the old value of that variable, and anything that is directly proportional to that must change the same way. Multiplied, it too changes by exactly the same factor. So in our drag force equation, that's an example of direct proportionality, because because it looks like that. The y variable corresponds to the magnitude of the drag force. C corresponds to all the constant factors in the drag force equation, and then our other variable is everything else here on the right-hand side that isn't one of the constant factors. In other words, the variable that drag force is proportional to, have to be careful here, is velocity squared, not velocity. Velocity squared, not velocity. Velocity squared. So the way we write that is like this. The drag force is proportional to, that's what this symbol means. Drag force is proportional to velocity squared. So in other words, when velocity changes, then velocity squared changes by some factor, and then the drag force will change by the same factor as velocity squared changed. Let's take just the simple example. So originally, something is moving through the air and the drag force it feels is 50 newtons. And that's when the speed has just some value that we'll call v1. And now let's say the second value of v is twice that. Let's say a ball has now fallen a little bit more, and while falling it accelerates, and now it's got twice the speed. So drag force is directly proportional to v squared. We know that v itself changes by a factor of 2, but to use the proportionality idea, we have to see how v squared changed, because it's v squared that is proportional to the drag force. Well, we can figure out how v squared changes pretty easily from this, just by squaring the whole equation. Square the left-hand side and square the right-hand side. So left-hand side squared is just the square of v2, and then the right-hand side, square everything, so that's a 4, and then this is the square of v1. So in this case, when the speed itself changed like this, velocity squared changed by a factor of 4, and since it's velocity squared that's proportional to the drag force, then drag force must change by a factor of 4. So the new value of the drag force is 4 times the old value. 4 times the original value, which was 50, so now the new drag force is 200 newtons. Okay, now let's try it one more time here. Say again we watch the ball fall, but we don't watch it for quite as long. We don't watch it until the ball has doubled its speed, but now the speed is just 50% greater. So when we first started watching the ball, the drag force was 50 newtons, and that was when it had the speed we call v1. Now the later value of velocity is 50% larger than that, or 1.5 times that. And again, to figure out how the size of the drag force changes, we need to know how v squared changes, because those two variables are proportional to each other, meaning they must change the same way, exactly the same way, by exactly the same factor. And again, we figure out how v squared changes by squaring our v equation. So the second value of v squared equals all this squared, which is 1.5 squared times the first value of v squared, the original value of v squared. Well, 1.5 times 1.5 is 2.25. So when v increased by a factor of 1.5, v squared increased by a factor of 2.25. And this variable called v squared is the one that's proportional to the magnitude of the drag force. So the drag force changes by the same factor, 2.25. So the new magnitude of the new drag force is 2.25 times the magnitude of the old drag force, and the old drag force was 50, and then that means the new drag force will be 2.25 times 50, which is 112.5 newtons. In the lecture exercise, you'll have a couple other simple proportionality questions similar to this. The one thing that's a little tricky to get used to, but it's important to get used to it, is that the name of the variable that is proportional to drag force is v squared. V squared is just as legitimate a name for a variable as v. V squared is just as legitimate a variable as v. And in this case, the relevant variable is called v squared, not v. Okay, now it turns out that when there is a drag force, there is this other phenomenon called terminal velocity. Let's see what's going on there. So, let's say you drop a ball and it falls through the air. So dropping it means that the instant you drop it, and say that's the time when you turn on your stopwatch, so time 0, at that moment it starts from 0 speed and starts to accelerate. Since it starts at 0 speed and the drag force is proportional to the square of the speed, that means when there is no speed, there is no drag force. So at the instant you let go of the ball, the only force on the ball is its weight. And of course, if that's the only force on the ball, then that's the net force on the ball. And then that net force is responsible for making the ball accelerate. But remember, if gravitational force is the only force on something, you've got free fall, and you know what the acceleration is. In free fall, it's 9.8 meters per second pointing straight down. Or for shorthand, we always call that g. Now, imagine some time after 0 seconds. The ball has had a chance to gain some speed, so now it feels a drag force. V is no longer 0, so magnitude of the drag force is no longer 0. The weight is still there, the weight is still the same, the weight is still mass times g. But now there's a drag force. The drag force points opposite to the direction of motion. The ball is falling, so direction of motion is down. That means drag force has to point up. And it's still a relatively small drag force because we're imagining at this moment the ball has not had a lot of time to speed up very much. But the drag force then, opposite to the weight, is able to cancel out this much downward force, so that the net force is just the remaining downward force that hasn't been canceled out. So now the net force is smaller than it was here, which means the acceleration is smaller here than it was here. There still is acceleration because there still is net force, but it's a smaller acceleration. So I'll draw it with a shorter arrow. And it's a smaller acceleration, so now whatever that acceleration is, we know it's got to be less than g. Now let's look at a later time. After this, there's still acceleration and net force. That acceleration is in the direction of velocity. The ball is falling. And we know anytime velocity and acceleration point the same way, you still speed up. So the ball is still going to speed up, just speeding up with less acceleration than it had at first. So now, at some time later than time 1, there's still the weight, and it's still the same m times the same g. That force isn't changing, but the ball has been speeding up between time 1 and time 2. So when speed gets greater, drag force gets stronger. So drag force is stronger than it was before. So it cancels out more of the downward force, and the remaining amount of force is the net force, the amount of downward force that's left over. And since there's still net force down, that means there's still acceleration down, but the net force at time 2 is smaller than it was at time 1. So the acceleration at time 2 is less than it was at time 1. Okay, now let's look at an even later time, sometime after time 2. The weight is still there, it's still the same. The ball has been speeding up, but let's imagine now that it speeds up quite a bit, makes the drag force quite a bit larger, and in fact now it's made the drag force this big. Right? The velocity has kept on increasing, so the drag force has kept on increasing, and when it keeps on increasing, eventually it'll be just as strong as the weight force. And now that the weight force and the drag force have equal magnitudes, and they're pointing in opposite directions, the net force is now 0. And that, of course, means no acceleration. The ball stops speeding up. The ball is no longer accelerating. It just maintains the same speed that it had at this instant when the acceleration went to 0. So there's called the velocity at time 3. And it's going to keep that velocity because there's no more acceleration, there's no more change in the velocity. That's what no acceleration means. So think about just one more time, sometime after time 3, time 4, sometime after time 3, the weight is still there, same as always. There's been no acceleration, so there's been no change in the velocity since time 3. Since velocity has not changed, the strength of the drag force has not changed. So its strength of the drag force is still what it was at time 3. It's still equal to the weight. So net force is still 0. Acceleration is still 0, meaning the velocity has not changed since time 3. So at time 4, the velocity is still the same as it was at time 3. The velocity is no longer growing. The velocity stays at this value for the rest of the time that the ball is falling. And we call that terminal velocity. Because of drag force, the ball speeds up, but eventually gets to a velocity that it won't get beyond. When it reaches that so-called terminal velocity, it stops speeding up and continues then to fall at the same velocity all the rest of the way. Think about what that looks like graphically. We still want to be thinking about velocity graphs and acceleration graphs and all that. While the drag force was increasing, it was canceling out more and more of the downward force, and so there was less and less downward force left over to be the net force. The net force was decreasing, so the acceleration was decreasing. And let's say the direction of motion is, we'll call the positive direction. So when there was net force, it was always pointing in the positive direction. When there was acceleration, it was always pointing in the positive direction. But as time goes by, it gets smaller until eventually you get to that point where the drag force is just as strong as the weight, which points in the opposite direction. So those two equal and opposite forces cancel each other out, and there's no more net force, which means there's 0 acceleration from that time on. So what does a graph of velocity versus time look like if that's the acceleration? Well, remember, on a velocity versus time graph, slope is acceleration. So this graph tells you about the slope on this graph. So for the first part of the time, you've got positive acceleration but decreasing all the way to 0, which means here you have positive slopes, but they're decreasing until they get to 0 slope. So changing slope means a curve, and then the slopes of the tangent lines are the slopes that are decreasing until they get to 0. So it looks like that. That velocity is increasing, but it increases at a slower and slower rate. The acceleration is decreasing. That is, this tells you about the slopes here. Right? Early in the fall, the slope is positive and large. Later on, the slope is still positive but smaller. Later on, the slope is still positive but very small. Eventually, the slope is 0. You get to a flat line on the velocity graph, slope 0, corresponding to 0 acceleration. The falling ball will stay at this velocity for the rest of the fall. That's the terminal velocity. The velocity that it gets to and then stays there. The last velocity that it has before landing. One last thing, let's think about this, not not graphically, but a little bit algebraically. So we got these two forces acting on the ball, weight and drag force. And we're saying the positive direction is the direction of motion. So the weight is pointing in the positive direction, drag force is pointing in the negative direction, and now we want to think about how those forces combine to give you the net force. And remember the slogan that I mentioned in the last video, to get the net force you just add all the force in the positive direction and subtract all the force in the negative direction. That's a slogan worth remembering. So net force is all the force in the positive direction, that's just weight, minus all the force in the negative direction, that's just drag force. Since that's a net force, you can set it equal to mass times acceleration. So mass times acceleration is the net force, and that's weight minus drag force. Let's write weight as mass times g. Now, let's rewrite this as an equation for acceleration. That is, we want an equation that says acceleration equals something or other. That we want just acceleration on the left-hand side of the equation. So we divide everything by mass to get mass out of the left-hand side. So what we're left with then is acceleration equals, right, we're dividing the whole equation by m, so we have mg over g, that's just plain g, and then minus drag force over m. And now we see something something interesting, that if an object has large mass, then this denominator is large and this fraction is small, which means you're subtracting very little from g. So that means a will be less than g, but not too much less than g. So a is close to g, but less than g, but still pretty close to g. Then, if the mass is small, on the other hand, if this mass gets smaller and smaller, the denominator gets smaller and smaller, so this fraction gets bigger and bigger, which means you're subtracting bigger and bigger numbers from g. You're subtracting more and more from g. So after subtracting more and more from g, the actual acceleration is less and less. Sorry, a should be less than g. And if mass gets really small, then acceleration might be even much less than g. All right, we'll think about that more in class.